not your idea of a Valentine's Day gift, I guess, but here we are on Valentine's Day Eve, and I'm going to tell you about the Extrema and the first derivative test. Get the pen to working here, and we'll be on our way. So here are some of the things we're going to talk about. Relative extrema, first derivative test, to find relative extrema, absolute extrema on closed intervals. We've got a little trick there that you have to be careful for, and getting maximum and minimum values of real-life models. And that's one of the biggest deals about this one, because you want to find minimum and maximum values. Just for example, if you have a business, you want to keep those costs low. Minimum, that sounds good, right? Revenue, you want that as high as possible. Better yet, you want profit as high as possible. Alias, maximum. Let's get with it. Relative extrema. All right, why relative and why not the real thing? Why not absolute extrema? By the way, extrema means maximums or maxima and minima. Why relative? Why do you throw that in? Well, it's because you're usually working with intervals. Why are you working with intervals? Because some numbers for x, for example, do not make sense. X represents how many of something you're selling or making. Okay? What's the deal about that? Well, suppose you're talking about computers. Can you possibly make a negative number of computers? No. So your interval starts at 0, whether you think about it or not. What the maximum is, you're going to have to ask the people on the production line, how many, at the very most, can those machines make in one day, or 1 year, or 1 week, whatever it is you're interested in. So there will be a maximum, and there will be a minimum of quite often 0, for obvious reasons. So here we go. We're going to keep this concise, and I'm going to send you a copy of these altered slides because I've made quite a few changes. If you looked at the last ones by any chance, probably only one person has, but you'll see that there's some differences to emphasize some things that I want to make sure you don't miss. So here's an example of a function. You can see the curve going there, and let's see if the pen's going here. There's my pen, good. So your curve is going like this. Gets to a high point, starts decreasing, gets down to the bottom, starts increasing again. Comment. This maximum and minimum are all about the y value. In some circumstances, the y value might be the revenue, it might be a cost, it could be all kinds of things. I usually only mention about the cost, revenue, and profit, but there are other things too. So let's make this a little bit simpler, or keep it as simple as we can. First of all, I talked about why you have intervals. So on an interval, C represents some x value, and that C is going to be a maximum in that interval if, when you put C in your function, you get the biggest value anywhere on that interval. Remember, these are y values. This is where you hit the top, so to speak. And this says all the rest are either the same or smaller than that. Check that one off. Part 2. We're talking about C being an X value, and it's going to be a minimum, and we're talking about Y values, just on that interval, not everywhere, on the interval, so that when you put that particular value in and find your Y coordinate, that is actually the smallest you're going to find for any Y value on this interval of x's. If it's either a maximum or a minimum, it's said to occur at x equals c, where c put in the function gives you the biggest y value or the smallest y value anywhere on that interval. So let's get started on how we can find that. So I hope I've emphasized those. It's got a relative maximum or minimum at x equals c. That's the critical number. And at that point, one of two things is happening. Either the derivative is 0 for that c, or the derivative is undefined at that c. Keep that in mind. Next, the first derivative test. Notice back here, I was talking about the first derivative on that last part at the bottom. First derivative test. Now here's where I've added some things of my own to make sure that the important parts didn't get blended in with that gray or green background. So we're talking about the first derivative test, so of course we're talking about the derivative, just the first one in this section, 3.2 or 3-2, whatever you want to say. We're talking about an interval from x equals a to x equals b, so it might be like 7 to 19, 0 to 5, whatever. If your derivative is negative on the left, these two go together. If the derivative is negative on the left and positive, now this is sort of tricky because of the way this is, and positive, positive on the right. Negative on the left or positive on the right. Not both, it can't be both. If it's either one of those, you've got a relative minimum. Now this means that the derivative being negative means it's going down, and on the right side it's going up because the derivative is positive. That means it must have been at a low point in between. And there's your relative minimum. And the second part is saying the same thing except reverse. You're talking about an interval, yes, and if the derivative is positive on the left, so these two things go together, positive on the left and negative on the right, that's the derivative. You're going to have to test to see what it is. We'll get to that. If it's got both of these attributes, positive on the left, negative to the right, that means you got a relative maximum. And for the particular application, that's going to be interesting to you or critical to you. Third, You might not think this is important, but it does have an importance, although it is lesser than the other two. If it's positive on both sides or negative on both sides, then that place that you are looking to be a maximum or minimum is neither one. It's the same on both sides, the derivative. If the derivative is both positive on both sides or negative on both sides, then you do not have a minimum. Where's my marker here? It's not a minimum, and it's not a maximum. So even though this is sort of a negative comment, it's still important in its own right. So take note of that. Next, here's some pictures. This first one is where the slope is negative, alias derivative, and positive on the other side. In other words, it changes values of the derivative on either side of this critical number. If it changes signs, if the derivative changes signs from negative to positive, you've got a minimum in that interval. If it changes signs in the other direction from positive to negative, then you've got a relative maximum on your hands. And you've got two examples down here where the slope is positive on one side, positive on the other side. You don't have either a maximum or a minimum on that interval. Or it could be negative on both sides. You don't have a maximum or a minimum. Sorry about that. So, guidelines. Number one. Big surprise, right? Find the derivative of the function. You're going to set those equal to 0 to find out where those critical numbers are. Critical numbers are where the derivative equals 0, or where it's undefined. You might have a denominator that's 0. Those are going to be critical numbers. You're going to test the sign of the derivative. Now these critical numbers are going to split the number line just like as if you took a knife to it and cut it in pieces. Take a scissors, cut the number line up. If you have, here's your number line. If you cut it here and cut it here, those are critical, where the critical numbers are. If you cut it two places, that gives you 3 intervals. You've got numbers out here, you've got numbers between the critical numbers, and you've got numbers to the right of the last critical number. 3 areas. What you're going to do is, and you have a choice here, pick any number at all in this interval. Put in the derivative and see if you get a positive or a negative. Go over to the next one. Pick one of these numbers in here, any of them, put it into the derivative again, see if you get a positive or a negative. Then you go to the third interval, and as many intervals as you need to. Pick any number in here you like. Anything you like, your choice. Put it into the derivative, find out whether it's got a positive or negative value. Note that it won't be 0. It has to either be positive or negative. The 0 values are what give you the critical numbers. The signs in those intervals tell you what the derivative is, what the function is doing. For each critical number, you're going to decide whether it's a minimum or a maximum on that interval, or maybe it's neither one. So here's an example so we have something to play with, something to talk about. So we've got x to the fourth minus x to the third, or x cubed. Make sure you write it down properly, of course. Take the derivative. That's what you got up here. There's your derivative. And this is the same thing, just in a different form. Because remember, what you're going to do with this derivative is set it equal to 0, which will give you the critical numbers. Looking ahead to that, you know that having it factored like this is going to be a big help, because when you set that equal to 0, you're going to set that equal to 0 and that equals 0 using the zero factor property, and that'll give you your critical numbers. So doing that, solving for x, you get two critical numbers. Now notice what that's going to do. Visually, here's your number line. Zero's in here somewhere. 3/4 is in there somewhere to the right of that. The important thing I want to point out is that that splits the number line into three sections. Numbers back here, numbers between the two critical numbers, and numbers to the right of the second one. Three areas. Then what you're going to do is you're going to pick any number that you like in that first interval. Say you pick a -7. You'll put that in here and find out whether you get a positive or a negative answer, period. You're going to take a number in the second interval. Now that's a little bit narrow, but there's always something in there. You might pick 0.1, for example. You put that in x, in the derivative, see whether it's positive or negative. You don't even care how big or how small it is. It's only whether it's positive or negative. Third, you're going to take some number that you find interesting over here. Maybe your favorite number is 17. So use 17. You put that into x in the derivative. See whether you get a positive or negative answer. Remember, those test numbers that you pick will never give you zeros because you already figured those out. Those are the critical numbers themselves. Those are your test values, and you have almost infinite, well, you do have infinite latitude in picking those x values. Here's an example of what someone else did. First of all, up here, this is our interval number 1. That interval goes from -infinity up to 0. Remember, I said you can pick anything you like. This person picked -1. You don't have to pick -1. You can pick -1,562 if you like. It doesn't matter. And you're going to take that, you're going to put it into the derivative. Take that number, put it into the derivative, and see what you get. And you don't care what the magnitude is. The only thing you care about that is that it's negative in this case. If you pick another number in that interval, it's still going to be negative. They all are. That's why you can pick anything you want inside that interval. Second part, this is the second interval, and this person picked 1/2. That makes sense. But you could have picked anything. You could have picked 0.7, for example, because it's in here. You could put it in your derivative, and all you care about is, oh, you end up with a negative number here. That's what counts. Not the 1/4 part, only the fact that it's negative. And third, you have this third interval, which seems bigger than the other ones. You can pick anything in there you like. If I'm going to pick one, since I don't have to do all this manually, maybe I'll pick a 42. Maybe that's my favorite number. And I'll put the 42 in here. This person picked a 1 because it's nice and simple. You can actually do the calculations sometimes very easily by picking a particular test number. Again, put that into the derivative. See what you get, positive or negative. That's all you care about. Where it's negative, that means the function itself, not the derivative, the function itself is decreasing. Negative here means the function itself is decreasing. Positive here means the function itself is increasing. I think I've said enough about that. There's a picture of that function in case you're curious. If you waited that long, and now what would really throw me would be if you paused the video about a minute ago, ran to your calculator, graphed it to see what the thing looked like. That would be neat. That would be really exciting. If you didn't, no problem. Here's the picture. You can see what's happening on that first interval. Where's my pen? On that first interval, the function is decreasing, just like we said. The second interval, it's decreasing again. When you have a critical point like this, quite often it goes from increasing to decreasing or vice versa, but not all the time. This is an example of where it's not so this time. It goes from decreasing to decreasing on the next interval too. But after that, you can see what's happening is it's increasing, just as we saw with our analysis. A little bit of a reminder here too. So what we found over here was we had the relative minimum at 3/4, but that means the relative minimum is at 3/4. It's not the relative minimum. The actual relative minimum is this number right here. The minimum or maximum is always the y value. Don't get them mixed up. The x's are important. They point you to the y values, but they're not the maximum or minimum values. So try to make sure you get that straight. I wouldn't suggest getting a tattoo with it on to remember, but do something, maybe carry around a piece of string or something to remind you of that for a couple of days till you get it straight. Notice that the critical number x equals 0 did not give us an extremum because it was negative on both sides. We saw a picture back there. If you want to see it again, you can back up. And if I don't forget, I'm going to send you a copy of this my own set of slides, as soon as I'm finished here. Absolute extrema. Now we were talking about relative extrema, which are inside a particular interval. And I talked about why we're talking about intervals instead of everything under the sun. So first of all, this is a little bit more important for people taking Calculus 1 or Calculus 2 or one of the others. The function has to be defined on the interval from a to b, and the c has to be somewhere in that interval. And that's pretty simple. It's something that we're not likely to violate, but is a concern. So first of all, we've got an absolute minimum if at that value is C, let me get the arrow there. If this C value, when you put it in the function, is smaller than all the rest of the function values in that interval. Notice the negative sign. This represents all the y values in the interval. This says no matter which one you pick, it's always going to be at least as big as f of c. This is the smallest, and all the rest of these are either equal to it or bigger. And a relative maximum says pretty much the opposite. There's a point, x equals c, it'll be an absolute maximum. That means it's at least as big as all the rest of the y values in that interval. Last, just a small note, is that if we just say minimum or maximum of that function, we're talking about absolute maximum or minimum. If we're talking about relative maximum or minimum, we always use the word relative. If we don't use the word a modifier like that, then we're talking about the absolute minimum and maximum. There's a picture. We've got a relative maximum. Notice relative-wise, we've got a relative maximum because in this section, we've got a highest point. In this section, we've got a lowest point. So it's a relative minimum. But this value up here, this y value, is bigger than any of the other ones you see from A to B. So it's an absolute maximum. Notice something different about this one. You're going to check out the endpoints as well as the critical points. So what you're going to do is you're going to make a list. You're going to find what is y here, y sub 1, your first y value. What's your y value there? What's your y value here at the critical points and at the end points? Take a look at those four. Which one's the highest? Which one's the lowest? Those will be the absolutes. So notice this last point. I mentioned it earlier, just a minute ago. Extrema can occur at the endpoints. So when you're looking for an absolute maximum or minimum, you not only check the critical points, you check the endpoints as well. Include those in your analysis. Now, in regular calculus, as opposed to business calculus, you're going to be more concerned with theorems, maybe proving some things. On this one is just here to tell you something that might seem obvious, but might not be. If f is continuous, in other words, we're not picking up the pen as we graph the function. If that's true, then when you go from A to B, as you're drawing your graph, f will have a minimum value and a maximum value. It might be at one of the critical points, it might be at the end points. So you have to check out the critical numbers and the end points. Both. Don't forget the endpoints. All right. So some guidelines. We've sort of talked about most of these guidelines, but here are some steps. You might want to write these down. So when you go to find the extrema and you think, okay, I know so much stuff where do I start? So go back to this. First of all, find the critical numbers. That means you're going to take the first derivative. You're going to set it equal to 0 to get the critical numbers, where the function has a derivative of 0 or it's undefined to be the critical numbers. That's going to split the number line into several different sections or intervals. In each one of those intervals, you're going to grab a test point of your own choosing, evaluate what f is at those critical numbers. Also evaluate it at the end point. All of those are important. So you get a list of function values at the critical numbers, function values at the endpoints, and then you'll just breeze through them visually, which one's the highest, which one's the lowest. That part is easy. Actually, it's not too bad anyway. So let's hit an example. So we've got an interval from 0 to 5. And going back to what I said earlier, why an interval? Well, maybe this is the number of TV sets or something that you make. Maybe you're a leather worker, and you can make up to 5 purses per day. Well, you can't make a negative number of purses, so the interval starts at 0 because you maybe make 0 today. Maybe you make as many as 5, but you know you could never make 6 or more. So there's your interval and the reason for it. So you want to find the minimum and maximum values. So what do? Okay, start, write the original function, double check, make sure you wrote it down correctly, because if you don't, then nothing's going to work from here on. Differentiate that. In this case, it's pretty easy. Small reminder, if some of these things don't become automatic, if you can't go from this to this in the blink of an eye, you need to go back and get some more practice. This should become extremely easy by this point. Okay, back to the point. We're looking for maximum and minimum values, so we differentiate the function, critical numbers, set the derivative equal to 0. Simple as that, sometimes. Solve for x, and there's your critical number. That critical number splits the number line into 2 areas. Negative infinity to 3, 3 to positive infinity. And what you're going to do is you're going to check out your function at the critical number, find the function value, not the derivative, the function value at that critical number, and you've only got one to check out, but you also don't want to forget the endpoints, because even though they're not critical numbers, they could be a maximum or a minimum. So you put the endpoints in the function itself, see what you get. Put the critical numbers in the function, see what you get. And the other endpoint in there, see what you get. And just look at the 2, the negative 7, the negative 3. The biggest one is 2, the smallest is negative 7. You've got your numbers. The maximum is 2, the minimum is negative 7. Now remember, this is not the maximum. This points through f, it points to what the maximum is. The maximum and minimum values are function values. Or, if you want to say it this way, y values. So We've got a minimum on the interval and a maximum of 2. There's your graph. I would suggest, for fun if nothing else, when you do some of these problems and you get to the end and you see the maximum, minimum, or maybe a tangent line or whatever, just throw it into the graphing calculator. See how it really looks. To me, there's a great satisfaction doing all that work and then seeing that it all really goes together. And we've got an application to take a look at. And we want to do this because the minimum and maximum values are 2 of the most important reasons for taking calculus. Several years ago, when I talked to people down at the Johnson College of Business and Economics, that's the George downtown, I asked them what were some of the things they wanted their students to understand when they got out of the business calculus. That was one of them. Differentiating was another one. Very high on the list. Not the only things, but those were high on the list. Here's our example. And let's see. What's your name again? Okay. So it's whatever your name is. Hamburgers. Let's see. I'll pick someone's name, let's say. Oh well. Let's say, I was going to say Smith or Johnson. We've got Smiths and Johnsons. Well, let's see. Johnson comes before Smith, so we'll call it Johnson's Hamburgers. Anyway, put your name in there and call it that hamburgers. So someone has done some work for you. You probably paid them good money, and they've come up with a profit function for you. So here's your profit function. Notice that this is a capital P. And the small p, it's hard to do it right here, but remember that represents actually the unit price of an item. Big P for profit, small p for unit price. Just thought I'd throw that in. But anyway, someone's give you the profit function, and what you want to know is what's the sales level that yields the maximum profit. So you might want to check, okay, what are we doing right now? What did I see on the spreadsheet last month? What would we have to do to get the most profit possible? So maybe you talk to your sales people and you say, if we could get this up a little bit higher, we'd get a bonus at the end of the year. Something like that. So how would we get that? Well, we're talking about maximum, and that's what we've been talking about for a few minutes here. And to get the maximum, how are we going to do it? First of all, we're going to find the equation for marginal profit. Remember, this is profit. dP dx is the derivative of the profit. It's also known as marginal profit. And before we move on, there's the function, you can see it. Remember what the marginal profit tells you for one thing. At a certain level. Now, suppose you've got a production line. And suppose sorry about that. Production. So you're making X of these hamburgers. Maybe 1,000 hamburgers, 2,000, 3,000, whatever it is. At that level of production, whatever it is that you want to think about, if you put that X in there, what dP dx says is, if you go from making X of these hamburgers to making X plus 1, of these hamburgers. What does that do to the profit? Does it go up? Does it go down? How much? That's what it says. Make one more of whatever your item is, and what does that do for the profit? If we were talking about revenue, it would mean what does it do to the revenue if you produce or sell one more item? Same thing for the cost. Just thought I'd throw that in because they are important. So you're going to take that. Remember this, what you're actually doing is setting the derivative equal to 0 because you want to find the critical points. So you're doing some algebra here. And there's your critical number. Now remember, your interval was from 0 to 50,000, I think it was. And your critical number is 24,400. So this should be the maximum number of hamburgers, or the number you need to make to maximize your profit. So here's a graph of your profit function. It's probably a good idea to not just look at the function, look at our graphs too. That might give you an extra idea. Never hurts to have the eyes looking at something, because sometimes an eye picture tells you a little bit extra. So this is what it looks like, and there's that 24,400 hamburgers right at the top. Well, not right at the top, to the left or right. The top value actually tells you what the profit is if you sell 24,400 hamburgers. To get the maximum profit, you actually put that 24,400 into the profit function and just hit the calculator, really. Just a little bit of calculator ease here. Remember what I told you, take that 24,400, store that in X, and then type this in your calculator. Your calculator is going to use the 24,400 where it sees the X's, and it's going to tell you what the profit is for that level. Now, since that's the maximum profit, now always try to think about what these things represent. It means if you sell less than that, you're going to end up with less money as your profit. If you sell more than that, you're going to get less than that amount. Even though you think, oh, if I sell more hamburgers than the 24,400, I'm going to get more money as a profit. No, not in this case. And as a business owner, you have to know these things. And that is it. And so with that, if I've made a good recording this time, I'll say goodbye, keep smiling, and I'll see you next time. Have a good evening, and happy Valentine's Day if you see this in time.